Today we're going to determine the efficiency of a radiation detector. In this case I'm using the Gamma Scout, which has a little Geiger mueller tube inside, where you can see the window just in front here, a thin mica window. And we're going to use these radioactive sources with it to determine the efficiency. We're going to use strontium-90, which is a pure beta emitter, or rather pure beta emitter. And we're going to use barium-133, which is a pure gamma emitter. This will make a difference, as we will see in a second. As I said, this will be a Geiger mueller detector, and let's examine the sources. So the source, the actual radioactive source, is in the center here, in this bit, but of course it has a front side and a back side. So we can imagine that at least half the radiation will come out of the other side, as opposed to just the back side, of course, and it will come out the sides as well. We'll just verify this with our device. So let's hold one source in front with the proper side, and let's flip the source around. Okay, still a reading, and from the sides, yeah, still a reading as well. So if that is our radioactive source, there will be radiation coming out this side, from the front side, and from the back side, and from the sides as well. So we can imagine that if we have a Geiger mueller tube that is just measuring from one side here, and the Geiger mueller tube will actually be bigger than the field of radiation if we are really close to the source, like here. So we can imagine that we're probably getting close to 100% what is coming from this side, but it will still be less than 50% of the total activity of the sample, as there will be radiation coming out the other side and from the sides as well. So we'll try to verify this today. Also, as I said, we're going to determine the efficiency, and this largely has to do with the type of radiation emitted by these sources, gamma radiation or beta radiation. We will see that in a second. So, first of all, let's have a look at the sources. What does it say? It says barium-133, a gamma emitter produced in September 2008, where it had an activity of 1 microcurie, and it has a half-life of 10.5 years. So within 10.5 years, that activity will be reduced to half the activity. So it will be 0.5 microcurie after 10.5 years. Now let's have a look. What is the microcurie? The microcurie is the unit that determines the activity of a sample. The curie equals to 1 gram of radium. So 1 curie means 1 gram of radium-226. That was back from the time where having 1 gram of a radioactive material wasn't so uncommon, and it was named after Pierre and Marie Curie, who discovered radium-226. However, this unit is kind of bulky, so we're going to convert it. So 1 curie also equals to 3.7 times 10 to the power of 10 becquerel. Now the becquerel, let me try and write it. It's French, so I'm not sure if I'm saying it right, but still. The becquerel is a unit that determines the amount of decays per second. So becquerel is decays per second. So our little source here has 1 microcurie. That's 1 multiplied with 3.7. multiplied with 10 to the power of 10, but as this is micro, you know 10 to the power of minus 3 would be milli, and 10 to the power of minus 6 would be micro. So it's microcurie, that's why we need to multiply this with 10 to the power of minus 6. So we can do this. 1 multiplied with 3.7 is still 3.7, multiplied with 10 to the power of 10, multiplied with 10 to the power of minus 6 will be 10 to the power of 4. So let's calculate 3.7 multiplied with 10 to the power of 4. So first of all we're going to remove that decimal point. 10 to the power of 1, 2, 3, 4. So we got 37,000 becquerel in here, and that equals to 37 kilo becquerel. Kilo is 1,000, so you can remove these and make it into 37 kilo becquerel. So 37 kilo becquerel equal to 1 microcurie, but we have to take more stuff into consideration. As you can see, the half-life is 10.5 years, and the source has been produced in September 2008, so it's a little old. Let's see what we can do. Okay, so we just determined the activity of 1 microcurie, which means the initial activity, so that will be called our activity 0. The activity at the time of production was 37 kilo becquerel. So what we want to determine is the activity at the currently given time. We will have to take into consideration, of course, the half-life. So let me just write down how to do this. We've got our initial activity of 37 kilo becquerel multiplied with E, that is the Euler number. It's a constant, so you don't have to worry about it. You just have to type it on your calculator, basically. It's just a mathematical constant. To the power of, in this case, the negative natural logarithm divided by the half-life. The T stands for time, half, so that's the half-life, multiplied with the time that has passed, T. We will still have to calculate this. So the source was produced in September 2008. Now it's May 2011. That is equal to 56 months, and that is equal to about 4.667 years. A stands for annum, that's Latin for years. We're going to have to convert it to years, as our half-life will be given in years, in 10.5 years, which we will have to use here in our mathematical equation. So, let's see. It will be 37 kilo becquerel, multiplied with that Euler number, constant, 4.667 years. The half-life, actually we can replace the half-life in that formula already. 2.5a to 4.6a. Okay, so let's type this into our calculator. Let's start with the logarithm, and then divide that by the half-life, which is 10.5 years. Then we will multiply that with the time that has passed so far, 4.667 years. Then we're going to have to negativate this. And finally add the Euler constant. And then we're going to have to add the 37 kilo becquerel, our initial activity. Well, multiply it with the initial activity. And that equals to 27.18. So 27.18 unit will be kilo becquerel, of course, as we used it here. So the total activity of the source will be 27,180 becquerel, which equals to decays per second. Can't write. That divided by 2 will be 13,590 impulses we could sort of estimate coming from one side of the source. Well, it will be likely less than that, so we could, well, estimate it to be maybe 12,000 impulses from that side, or less than that. We could say less than that, maybe. So, let's see. So, I did this calculation again for the strontium-90 source, which is 0.1 microcurie and has a half-life of 28.8 years. So 0.1 to multiplied with that Euler constant, I think 8 years, multiplied with 4.667 years, will equal to 3,306 becquerel. By the way, if you wanted to find out the activity of a source prior to this date, and let's say 3,700 becquerel was the activity of the source today, and you wanted to find out what the activity was 1 year ago, then you would simply have to discard the minus, the negative leading sign here, and apart from that, just multiply it with, well, would be 1 year now, and do everything exactly the same except for the leading minus here. And that is all. If you wanted to calculate an activity how it has been before. For strontium-90, which is a beta minus, or electron emitter, we have a current activity of 3,306 becquerel. The half of that, which we can sort of estimate to be coming from the source at one side, would be 1,650 impulses per second. Probably less than that, maybe around 1,500 or so. And barium-133, which is a gamma emitter, as it decays due to electron capture, has a current activity of 27,180 becquerel, and the half of that is around 13,590 impulses per second to be expected from one side of the source. Will be less than that. Well, let's see. But what we of course have to take into consideration as well is the background radiation, which we are going to have to subtract from our actual readings, just as we will measure the sources. Place it here. And measure the activity for 1 minute. I will be measuring the background radiation in 1 minute. We got 27 impulses a minute, so we'll write it down. 27 impulses for a minute. And to be even more accurate, it will be good if you could measure like the impulses for 1 minute, like maybe 10 times, and then take the average of that, so you will have an average impulses per minute. But I'm not going to do that right now because I'm rather short on time again, so we'll just take those 27 impulses per minute for granted, as it's not that much anyway compared to the activity of the sources, and shouldn't make that much of a difference. But to be accurate, you'd have to get more readings and then use an average in your calculations. So what I'm going to do now is place a radioactive source, barium-133 we want to measure, in the exact same location, and then set the device to measure again. So the gamma scout is right on the source. Now I'm going to press the button here. We'll just wait 1 minute to get the total amount of counts. Okay, so as 1 minute has passed, we recorded 993 counts or impulses. 993 impulses per minute. Gonna do the same with the strontium-90 source. Okay, so I'm repeating the same for that strontium-90 source. And we'll just wait for a minute. Okay, and after 1 minute, we have 11,410 impulses. Okay, so we have to take our impulses minus the background radiation, and we'll be left with the actual real impulses we got from the source, roughly. Divide that by 60 because we were taking the activity in becquerel, which is decays per second. So we're going to have to convert our units to impulses per second. We got 16 impulses per second from the barium and 190 impulses per second for the strontium. So for strontium-90, we actually expected around 1,500 impulses per second on that one side of the source. In reality, we got 190 impulses per second, so that equals to about an efficiency of 12.6%. And for gamma radiation, we expected 12,000 impulses per second. For real, we got 16 impulses per second, which equals to 0.13%. Now there's an explanation for why this is the case, because beta radiation is directly ionizing radiation and gamma radiation is indirectly ionizing radiation. To explain what's really going on there, I recommend that you watch my other videos where I already explained this. So this video doesn't get all that long anymore. If you don't know what that is all about, please just check the other videos, which I'm going to link right here in a second. Should be here, I hope so. So you can check it out. Anyway, with our beta source, we got 12.6% of the activity. So, well, it should actually be at least 80% or more, like nearing 100% for that Geiger-Mueller counter. So probably we didn't take the geometry of the beam into consideration properly. Maybe it was more like this, and our counter surface was like this. So we didn't measure the whole beam. Or it was more like this. Who knows? Maybe there was more coming from the sides than we would have expected from the total source. Or maybe it's just that the efficiency of the Geiger-Mueller tube is down because it has been overused and it has basically reached the end of life, which is a maximum of 10 to the power of 12 ionizations for a Geiger-Mueller tube with a halogen quenching gas, and about 10 to the power of 9 for a Geiger-Mueller tube with a organic component quenching gas, but should be about 10 to the power of 12 for the Gamma Scout. But we might have reached that already, so the efficiency of the detector is worse than it is supposed to be for a Geiger-Mueller tube, or the geometry of the source is not appropriate. But anyway, we just got 12.6% of the expected activity from the strontium, from the beta source, and just 0.13% of the activity from the gamma source. Well, it should be around 1 to 2% in a typical Geiger-Mueller tube for the gamma radiation detection at this energy. If you've got any more questions about the calculations or whatever, just let me know. I'll try and answer them as soon as possible. The problem is that I'm really busy lately, so in the worst case it may take a few weeks until I can respond, but maybe other people will respond to you before I can. Sorry about not being able to answer your emails lately, but I figured I'd rather use the free time today to produce in the video, so I might just still not be able to get back to all the emails I got at the time, so well, sorry for that.